Good morning, and thank you again for being here for the early session. I apologize for doing that at the last minute, but thank you for being understanding and patient. And here we are at 7 a.m. Of course, if you're watching later, then, well, welcome to your usual time. All right, so we had left off yesterday, so we talked about our PV equals nRT. So that was just like our quick, let's just summarize, right? So from yesterday, basically we ended up with those two equations. So we have our PV equals nRT, and we had all our variables for that. And then we saw that we could throw it into that other form, P1 V1 over N1 T1 equals P2 V2 over N2 T2. And so on Monday, we were just focusing on gases. But now we're going to look at phase changes. So we're going to talk about the energy that goes into doing these state changes, and then also look at those intermolecular forces. So on Monday, we had stated, okay, well, let's assume that gases don't have any interactions. So that was our kinetic molecular theory. We said size didn't matter. We said no interactions. Then we had our ideal gas laws. Again, that. But today, let's look into those intermolecular forces and kind of look, why are things, a gas at room temperature? Why is water a liquid? And look at all those questions. And so let's just start looking at what is a phase change in general. And we have our solid particle here. So I think it's easier if we put this in context of like water and ice. So, okay, our solid is ice. And we know if we add heat to it, it starts melting and turns into a liquid, right? Taking the shape of our container here. And then, of course, if you take that water and let's just say you put it on this stove, you start heating it up, and then you notice, right, it starts forming steam or its gaseous form. And then, of course, right, it starts boiling out of your pot, and you can see our gas molecules, right, occupying all of our space here and floating everywhere. But what we saw, so we were looking in the forward direction, and so this phase change in the forward direction was caused by adding heat. Of course, we could take that same water and steam and ice, right? We could cool back down our gas, reform our liquid in condensation, and then maybe stick this liquid back in the freezer and cool it back down to a solid. So we can see, right, we do phase changes by either heating or cooling our substance or changing pressure. And so, well, what kind of drives, again, the different boiling points? And let's take an example. So, for example, what dictates the difference between methane versus water? They're both pretty small. They both have some hydrogens. And why is methane a gas and water is a liquid? And so the answer to that is in these intermolecular forces. So let's define what an intermolecular force is. And so let's pay attention to So think of like interstate highway would be like between the states. And so same thing with these intermolecular forces. So these are, again, between molecules. And so let's compare this to intramolecular forces. So an intramolecular force is like the covalent bonds, the ionic bonds. And this is not what we're talking about. And so notice intramolecular is within the molecule. All right, so let's go back to looking at these intermolecular forces. And so all attractive forces are electrostatic in nature. So that just means that something has to be negative and something is positive. So look at this in more detail. And then the strength of those interactions determines the state. So we'll get back to that with our methane versus water example. And basically what we're going to get at, though, is the stronger the attractive forces are, then we're going to have a higher boiling point, and this substance may be either a liquid or a solid at room temperature. And so we'll see that these attractive forces vary, and we'll go through them. And so the stronger the attractive forces, the more the particles resist moving. So this just means right with each other. So kind of think of going from the liquid to the gas state. So if there are more intermolecular forces, right, it's not going to want to fly away. And again, really key point is we're talking about separating atoms, but we're not breaking any bonds. So I'm just starting this part where it says we're not breaking covalent bonds. And many people get this terminology wrong. That's why I'm really pointing it out. And then we will look at this trend. So the higher the normal boiling point, the stronger the intermolecular forces. And so again, why are molecules attracted to each other? We saw this in our ionic compounds, right? We had a cation, and let's just take sodium chloride, right? Our sodium was our cation, chloride was our anion. They were attracted since they're opposite charges, so there's your electrostatic interaction. But we can find that we don't have to have, complete ion to have these electrostatic interactions. So we can have them with a polar molecule, so we'll look at those. And so a polar molecule, kind of the key is that it has a permanent dipole. But again, we'll look at that in more detail. And then we'll find that even non-polar molecules have these temporary charges, and they call those instantaneous dipoles, which we will look at. And then, of course, the distance also makes or influences the factor. So the smaller the distance, the greater the force. And so generally, the Coulombic attraction, this is just in general, it's given by Q1 times Q2 divided by the distance. And so this is basically charge over distance. So again, smaller distance is greater attractive forces. So let's look at our weakest forces, so the dispersion forces. And so these dispersion forces have different names, so just be wary. So they could be called London dispersion forces, or just dispersion, like is shown here, or van der Waal. It's all the same. Or van der Waals. Okay. So anytime you see that combination, we're talking about our weakest forces. And so these interactions result from our temporary dipole, from fluctuations in our electron distribution. And so let's look at what that means. So let's zoom in on this little schematic here. And so let's just say we're looking at helium. So helium, nonpolar, right? Just a simple helium atom. And let's just say we could take a screenshot, just like a snapshot, and freeze them. And so let's just say that at this frozen moment in time, what if it just so happens that our electrons on one helium molecule are on one side? So here they're located on the left side. So that gives us a partial negative charge here. This empty region then has a temporary partial positive charge. And then because of this polarization, that might also induce the neighbors to kind of have that same effect. So what if, right, the electrons were also on the left side on this neighboring helium? So now, right, we see that intermolecular attractive force. Same thing with the next neighbor. And so this is where we get, again, our London dispersion forces from this temporary dipole. And again, it's temporary, right, because we've just frozen it. And so, of course, these electrons will keep moving round and round and round. So electrons, right, they don't stop moving, but you still have those temporary dipoles. And so obviously these are going to be pretty weak forces. And so again, every molecule has dispersion forces. It's just since they're the weakest, once we get into like polar molecules and hydrogen bonding, we tend to kind of just ignore the dispersion forces since they're a lot weaker. And so we can see the trend of molecule size. So this also goes with molecular weight. So I'm putting molecular weight there. So as we have increasing mass, right, our electron cloud tends to increase. And so that larger cloud is more polarizable. And you also just have more physical surface area to meet and interact. So we can just appreciate this boiling point trend. So beginning with helium, so it has a really small molar mass, boiling point of 4 kelvins, compared to xenon, which has a mass of 131 and a boiling point of 165 kelvin. So still pretty low. So still a gas, right, at our normal ambient temperature. But again, just appreciate the difference there. So size and shape also are an important factor. And so let's analyze this next scenario. So now we're trying to figure out, well, what drives the difference between this N-pentane and neopentane. So the first thing you want to look at is their mass to see if they're similar. And so yes, actually in this case, they're the same formula, C5H12. But then their boiling points differ. So pentane is 36 versus neopentane of 9.5. So this would be hard to work with at room temperature, right? That would start boiling. So not ideal. And so the difference between them is subtle, but we can see, right, our pentane is longer. So it's a straight change alkane. And you can see, right, they have a lot more surface area for interaction and they can stack nicely like that. So a lot of area for those intermolecular forces versus the neopentane structure where it's a compact ball. So there's not a lot of area for interaction. So, right, weaker intermolecular forces there. And so again, difference in boiling point. And you can just make a general note that branched alkanes have a lower boiling point. And so branch just means any sort of deviation from this straight chain. And so I could just draw an example. 1, 2, 3. 1, 2, 3, 4. So something like that, right? That's a branched alkane. So it's going to have a lower boiling point than N-pentane. And this is a nice graph because now we can see the trend with increasing molar mass of our N-alkane boiling points. So again, all straight chain. So they're all stacking nicely. The difference is in their molar mass though. So here the mass is plotted on the x-axis and our boiling point rises pretty linearly. All right, our next strongest intermolecular force is the dipole-dipole. And so this is anytime we have a polar molecule. And so our polar molecules, remember, they have a permanent dipole. And again, this suggests an unevenness in the molecule. And so both kind of the substituents and the geometry determine the polarity. And we've looked at this before. If you need help with this, reach out. We can always, revisit this concept. But basically, we're looking for something that has this permanent dipole moment. And so, right, this permanent dipole moment gives us those electrostatic interactions. And so now we're looking at acetone here. And so we have our C carbon double bonded to our oxygen. And so this oxygen, remember, is fairly electronegative. And so it gives us a partial negative charge here as our electron density is located to the oxygen. It's going to be pulling some away from that carbon. So I like these electrostatic potential maps since that kind of shows it a little clearer to us. So red area indicating a region of high electron density, and blue is low or kind of positive. And so with this permanent dipole, that means that this oxygen is attracted to the carbon end of another acetone molecule. And so again, you have your intermolecular force here, that electrostatic interaction. And so now let's compare these two molecules. So formaldehyde versus ethane. So formaldehyde was similar to acetone instead of the CH3 groups at the end, though it has just hydrogens. So it's even simpler. So it's our simplest aldehyde. And so the first thing I'm going to do before I look at anything else is let's just compare our masses. So very similar masses, different formulas. Okay, so we'll have to look at that more closely. And then look at the difference in boiling point. So formaldehyde is -19 versus ethane of -88. So what accounts for that difference? And if we look at ethane, right, ethane only has our London dispersion van der Waals forces. So pretty weak, while our formaldehyde still has the London dispersion, but also has, right, our dipole-dipole. And so just because of those dipole-dipole interactions, it makes a huge difference in the boiling point. So it's pretty fascinating to me. So we'd also mention that the dipole moment, so how polar it is, matters. So that's what's being shown in this graph. And so let's just appreciate it. So propane here is pretty much non-polar. So it has a dipole moment of 0.08. I would, again, say that's non-polar. And then we go to an ether group. So oxygen in the middle. So still polar, but maybe not as extreme. So then we go over to this oxide, which is in this triangle. So that kind of forces it into more polar geometry. Notice this electron density up there. Then acetaldehyde. So now our oxygen is more on one side, so even more polar, and again, higher boiling point. And then all the way to acetonitrile, where that nitrogen's on the end, and this nitrogen also, it's a lone pair. So again, fairly electronegative, that electron density map there. And so dipole moment of almost 4. And again, we're just appreciating the increasing boiling point as our dipole moment increases. And again, with these series, their masses are all pretty similar, so all pretty close to 44. So again, we're looking at the influence of the dipole moment with their boiling points. Questions on this one? And again, I know it's an early stream, so I may not be getting live questions. So just email me if there's any questions about the lecture. I'm more than happy to help. All right, so let's look at our next strongest force. So this is our hydrogen bonding. And so hydrogen bonding is the strongest. So of these 3 that we've talked about. And so this happens in a very specific scenario. And so if we look at these, so the elements oxygen, nitrogen, and fluorine are all extremely electronegative. And so when they're bonded next to a hydrogen, so let's just take HF. So that fluorine, extremely electronegative, basically strips off this hydrogen. And so remember, hydrogen just has one electron to begin with, right? And then it's involved in a bond. And then extremely electronegative element pulls it. And so that leaves our hydrogen to become de-shielded. And all that means is your proton is exposed. But because of this, it gives you a really strong partial positive charge on your hydrogen, and of course a partial negative charge on your fluorine, or any other case you see this. So again, it's in the case of OH, NH, and FH. So write that down, circle it, put it somewhere, highlight it on your periodic table so you know it's only when hydrogen is with oxygen, nitrogen, or fluorine. And let's look at, so they've shown ethanol here. So of course, any alcohol has this OH group. And we have our partial negative, partial positive, and then one hydrogen is going to be attracted then to the oxygen of another one. So there's our hydrogen bond. And so again, even though these hydrogen bonds are very strong, right, stronger than dipole and dispersion, they're still not as strong as a chemical bond. So just important to keep in mind. Let's compare these two boiling points. Now we're looking at ethanol versus dimethyl ether. So similar formulas, right? But these look like they're structural isomers, so different connectivity. And so our ethanol has that OH. So that means we're going to have hydrogen bonding. And, right, it's still polar, so we still have dipole-dipole. And still have London dispersion. So looking at ether, right, it is polar, so we do have some dipole-dipole interactions. And so that does bring us to a boiling point of -22, but no hydrogen bonding. So that ethanol has a boiling point that is much higher of 78. So pretty fascinating. And we could even throw, actually we're about to talk about water in this next chart, but I was just going to say, like, think about water. You know, it has even a higher boiling point than ethanol of 100 degrees Celsius. And a lot of that is all from those two hydrogen bonds. So quite fascinating. So this chart is showing our boiling points. And so there's methane again, so pretty low boiling point. Notice increasing along this group 4 with increasing molar mass. And then obviously right spot the anomaly. So that anomaly is water. So water has a much higher boiling point than expected. Again, all due to that hydrogen bonding. And ammonia is not on here, and neither is HF, but those would also, again, have much higher than normal boiling points. All right. So other related properties are surface tension. So surface tension basically right? The greater the intermolecular forces, the greater the surface tension. And so there's a couple of things that you could do to show this. And so kind of, again, if we were in class, I might do what's called my penny demo. And so with this penny demo, and you can do this at home, maybe if you have solvents, although maybe I shouldn't encourage you to play with organic solvents. But see how many drops of water can you get on a penny versus an organic, like pentane or something that's really non-polar. And so kind of the trick and what you would notice, and some of you have probably put how many, drops of water on a penny, but you notice that the water from all that hydrogen bonding and the strong intermolecular forces, right, it tends to beat up and kind of form this bubble. And that's again because of those intermolecular forces. So it's holding itself together. While something with weaker intermolecular forces, again, like pentane, you would not be able to fit as much, and it tends to, run off and, pull over, since pentane does not have the hydrogen bonding. So much weaker intermolecular forces, so it's not able to bubble up like the water. And so these are just numbers now for our surface tension. So C6H6, this corresponds to benzene, which is an organic. And so again, right, water, much higher surface tension from that hydrogen bonding. And repeating, so stronger the intermolecular forces, right, the higher the surface tension. And so other things that influence it, so if you were to increase the temperature, that would reduce its surface tension, which makes sense, right? So think about those intermolecular forces, they're together. But then if you add energy, right, that's going to start making them go further and further apart and stretch the surface, as they say here. And of course, what's really cool about surface tension is you can float things that would have a higher density on water. And so I'd like to show this video too. Once I pull it up. Oh, sorry.
Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk.
I mean, isn't that just awesome? All the power of surface tension. Of course, the lizard's moving pretty fast, but I think that's awesome. All right. And so again, the power of surface tension. So there's our paperclip floating or our lizard walking across water. So our next related property is vapor pressure. So vapor pressure is just defined as the pressure exerted by vapor when it is in equilibrium. And so what that means is, let's just say, right, any bit of water, right, there's still some water that's in the gaseous phase. So even even an ambient temperature, right, there's some water molecules kind of escaping. And then we see, okay, the weaker the attractive forces, the more molecules will be in the vapor. That kind of makes sense, right? And so if we have something that has really weak intermolecular forces, like methane, obviously it's already in the gaseous phase. But we could compare this. I start thinking about, and I know a lot of you are young and maybe aren't of drinking age, but if you've ever smelled, wine or something alcoholic, I always say it kind of hits you in the face. But what you're getting is that vapor, the ethanol vapors. And, we discussed that ethanol does have hydrogen bonding, but it's still has a lower boiling point than water with only one hydrogen bond. And of course, this vapor pressure also corresponds to its normal boiling point. And so this is a nice graph. And so like I mentioned, so things have some sort of vapor pressure until you hit the boiling point. But what does that mean? And sometimes I'll pull up another chart while we look at this. And so we're looking at this and we see increasing temperature. So it increases the vapor pressure. And so normal boiling is defined when your vapor pressure reaches your atmospheric. So 760 torr, again 1 atm. And so again, anytime that your vapor pressure equals your normal boiling point, then that is defined as boiling. So I wanted to just pull up this other chart. So now this is showing us the vapor pressure of ice, although I actually wanted water. That's not what I wanted. Here we go. This is a better chart. And so this is a chart that correlates the vapor pressure of water with temperature. So again, you can see it's exerting some sort of vapor pressure and then again, increasing. So this chart stops at 31, which is a little annoying. But again, could increase all the way to 100, and that what it establishes what normal boiling is. All right, let's go through the last part of this chapter, which is now the math and how to quantify the energetics of melting. So we said, right, energy has to either be put in or removed to do these state changes. But let's figure out how we actually quantify this. So this is a generalized heating curve. And so there's two different parts to it. So we have our heat capacity. So basically how much heat can our material take at a certain point. And then we have our state changes. So anytime you have a plateau on this graph, that means we're doing a state change. And so we have to put energy into the state change, and then we can continue on with the heat capacity. And so we'll go through this so it makes more sense. And so other bits of information that we need are both the heat of fusion. So the heat of fusion is the energy associated with melting. And so we can see the heat of fusion for a few substances here. So, and then our heat of vaporization is the energy needed to go in the gas phase. So evaporation, or again in the reverse direction, condensation. Notice that the heat of vaporizations are all larger than their heat of fusions, and that makes sense, right? So going from solid to liquid, you need only so much energy versus the liquid to gas is a much larger energy need to get it into that gas phase. And so as we look at this, so we usually look at the forward direction. And so if we're going in the forward direction, we're adding energy. And so melting, right, endothermic, so positive direction, adding energy. And then if you ever see a scenario where it talks about sublimation, so remember, sublimation is from where you go to the gas, to the solid phase, or vice versa. And if you're not given a delta H of sublimation, you can add your heat of fusion and your heat of vaporization, and that would be equivalent. So let's look at this heating curve. And these are, again, quantities that you would have to look up, or I would provide them on an exam. And so what I mean by that is, well, let's look at what we're doing overall. So our overall process is we want to take 1 mole of ice from negative 25 degrees Celsius all the way to its boiling point to boil it, and then take it to 125 degrees. But we have to do each segment at a time. So the first thing we're going to do is heat up our solid ice. So we're here on our leg, right? So it is a solid. And then what's also relevant is you need to look at the heat capacity for solid ice. So every material has a different heat capacity. And so the general formula is given here, but I always caution people, you have to just double check what your heat capacity units are. So generally, the heat that's required is equal to your mass times your heat capacity times your change in temperature. But it's usually like this because your heat capacity is given in joules per gram. So that's why it would be in mass. You could see your specific heat given in moles, though. So just watch out for that. So always double check your units. And so let's walk through this math. So again, we would have to look up this value. So this is a known value for our heat capacity. And so our heat capacity of ice is 2.09 joules per gram degrees Celsius. And then we're going from negative 25 to 0. So we have to stop at the state change. So that's really important. That's why we stop at 0. So of course, 0 is our melting point. So our change in temperature is 25 degrees. And in this case, your temperature, it doesn't matter whether you're in Celsius or Kelvin, because remember, Celsius and Kelvin go up the same. So it's only the difference that matters. So a 25 degrees difference in Celsius is also 25 degrees difference in Kelvin. All right. So now we have this set up. Let's just punch it in for good measure. So we can believe their numbers. So we have 18 times our heat capacity times 25. And so we get that we needed 940.5 joules. So they rounded to 9.941 kilojoules. All right, so now we're at leg 2. So this is our state change. So again, notice our plateau on our graph. And so we had to get the relevant heat of fusion. So the heat of fusion for water. And so that's 6.02 kilojoules. And notice the units. So now it's kilojoules per mole. And so now we just have to multiply it by our molar amount. So we had 1 mole of ice. And so it ends up being 6.02 kilojoules for that state change. Any questions on that? So we do the state change. So now, right, we're here on the graph. We just finished our state change. So now we're ready to heat our water. And so now if we're going to heat something, we should start thinking heat capacity again. And so that's what this is showing here. So we want to heat our water from 0 all the way to the boiling point. And again, we have to stop at the boiling point to do a state change. So there's our heat capacity formula. And so if you're somewhat familiar with water, you may know this heat capacity. So this is the one that people discuss, like when we're talking about the ocean being a big sink for heat and why it keeps us regulated and all that good stuff. And that is due to its high heat capacity. So water in the liquid state has a heat capacity of 4.18 joules per gram degrees Celsius. So just like we did before, convert moles to mass. So now we have 18 times our 4.18 and then times 100. And so that gives us 7,524 joules. And so rounding to 3 sig figs and then kilojoules, that gives us 7.52 kilojoules. All right. So now we're here, right? So now we need to do another state change. And so that is leg 4. So we have our water at 100 degrees Celsius, but now we need to do the state change from a liquid to a gas. So that's where we get our change in vaporization enthalpy. So how much energy that requires. And again, look at your units for delta H of vaporization. So 40.7 kilojoules per mole. So we just need to multiply it by our molar amount. So that's 1, which gives us 40.7 kilojoules for our state change. Just letting people soak that in. And again, right, it's what I like about this drawing is it was kind of drawn out to scale. So you can see, right, you have a large amount of heat added. So you have heat added on the X axis. So sometimes this is heat or time, which isn't always useful. I like the heat one. So this is really showing you how much heat you had to add to do that state change. So I think that's really key. All right, we're almost to the home stretch. So now we're here, right? We just completed the state change, but we said, let's take that same to 125. So that's what this last leg is. And once again, you have to find your heat capacity this time for steam. So again, little tedious, we'll say, right? Because you have to keep looking up all these values, or on an exam, I would provide them for you. So you won't have to be hunting on an exam. I'm just saying, in real life, if you ever wanted to calculate this, you have to look up all these values. And so our heat capacity still in joules per gram degree Celsius. So let's convert moles to grams like they did here. So now we have 18 grams times our heat capacity. So 18 times 2.01 times our 25, since we went 100 to 125. And so that gives us 904.5 joules or 0.904 kilojoules. And now usually at the end of it, it asks a question of like, what was the total energy of this process? And so for that, you just want to add everything back up, starting at our first segment. So now point, and I'm going to do this in kilojoules, so 0.941 plus 6.02 plus 7.52 plus 40. Ooh. So I'm telling you, that was a big one. Plus 0.904. And so that gives us a total energy of 56 kilojoules for that process. Any questions on that? Like I said, there may not be questions because we're early. All right. In the interest of time, I think I will end here. So I'll still be around by email. But like I said, I'm traveling out to do just some outreach today for a little bit during our normal lab time or lecture time. But I'll be back in the afternoon. So if you have any questions by email, I'll be watching and responding. And, if you feel lost, confused by this chapter, again, I'm happy to meet in person or over Zoom, whatever works best for you, whatever works best for your learning style. Just let me know. All right. And that's the end of week 8. So just keep that in mind. We're really barreling towards the end of the quarter here. So we have 2 more weeks of lecture and then our exams. So really, really flying by. All right. Thank you again so much for your hard work. You guys have been awesome. This class has been awesome. You guys are really putting it in hard work, good work. Keep turning in those assignments. That's really all I have to say is just keep up the good work. All right. Thanks again. And again, catch me by email if you need anything, and I will see you around virtually. So thanks again. As always, I appreciate it.